Okay, so it's time for the second core lecture, which is on the DHSS model. We did our overall intro and then we looked at understanding economic growth, and now we're getting on to natural resources and environment. And the key focus of the DHSS model is non-renewable natural resources, stuff we dig up out of the ground. Oil, coal, whatever, plus iron ore, phosphorus, etc., etc. Are we managing these resources well? What's going to happen in the long run? Oh, is the economy going to crash when they run out? These are the kind of questions we're interested in here. Okay, and that's the figure we looked at earlier. In the left-hand panel, we see metals extraction compared to global product. In the right-hand panel, we see primary energy use, again, compared to global product. And they're sort of normalized and on a log scale. So what we see is that the slopes of those lines are growth rates. So we see in both cases more or less constant growth rate, actually accelerating somewhat, and in both cases we have a more or less constant growth rate in global GDP and a similar growth rate in both extraction of stuff from the ground or metals from the ground and primary energy use. So they're growing at equal exponential rates. And you might argue, well, that's clearly not sustainable. And in the sense that it can't go on forever, that is definitely true. We'll come back to that. And some people who sort of famously said this is not sustainable were the Club of Rome, and in particular Meadows et al. In 1972, who published The Limits to Growth. And they basically said, we're heading for the cliff edge, and we're accelerating towards the cliff edge. So the most probable result of this will be a rather sudden and uncontrollable decline in both population and industrial capacity. And they were talking on a 100-year timescale. So they were talking about by around about the middle of the century we're currently in. On what basis did they draw this conclusion? Well, sorry, I've forgotten the order of my own slides. Before we go on to that, of course, it's not good enough to say that a trend is unsustainable if it can't continue forever. On that basis, we couldn't extract non-renewable resources at all, right? Because if we're extracting even a ton per year, say, well, in the end, that will lead to them running out. And the Earth is going to be inhabitable probably, I think it's for roughly another 1 billion years. So very likely, for any reasonable rate of extraction, it's not going to be sustainable across that whole time span. But that's not really a very good argument for just leaving everything in the ground. So what we want to know is whether our choices today will be condemned in the future. Broadly. More specifically, we might have particular criteria. One criterion could be future people should have at least the level of welfare that we have. Okay, that's the sort of non-declining welfare criterion, which is common in this literature. And according to Meadows et al., that criterion is unlikely to be satisfied, right? We're heading for a cliff edge. Welfare, population, we're going to have a massive crash, according to them. Okay, so on what basis did they draw that conclusion? Well, let's have a quick look at their model. It turns out it's a bit of a black box model, okay? So it's not easy to see how it actually works. But there are papers describing it and analyzing it, critical papers like Nordhaus 73, you can have a look at that. So what I'm going to do is just set up a really simplified, a super simplified sort of toy version, capturing some of the key ideas from the limits model. Okay, and here it is. So what have we got here? We've got, maybe I'll start drawing here. So we've got, I always get the wrong end of this pen. Households, firms, and a stock of oil, right? And the household sends labor to the firms, the production arena, so to speak, and firms produce goods. Why? But they can only produce with the help of oil. Okay? And this oil is free to extract, so it's just in the proper picture there's a tap, right? We just have to turn the tap on and choose what flow we want. And it's under pressure there, it doesn't cost anything to extract it. And Y is equal to the minimum of AL, L, and R. Okay, so this is a Leontief production function. I guess I talked about Leontief production functions before. I'm pretty sure I did. So Y is the minimum of this and this. So a classic Leontief case would be shoes, the number of pairs of shoes I have is the minimum of the number of left shoes and right shoes that I have, right? If I have 10 left shoes and 1 right shoe, I only have 1 pair of shoes. And in the same way, production is going to be, if these are equal, that's great, we're using everything. But if we've got 10 times more of this than this, well, 9/10 of this is just not used because this is the limiting input, right? There's no substitutability at all between these inputs. That's Leontief. Okay. Assume that the resource stock is finite and open access. What is the resource price? Well, if it's open access, and I haven't said that, but we've got loads of people here and loads of firms here, and this is just a free-for-all, there's no extraction cost, then the resource price will be 0. What is going to happen over time? Well, that depends a bit on AL and L. And we say we've decided that L is just 1, we've got no population growth. And AL starts at 1. So AL, let me get my notation right. AL at period 0 is 1. But in subsequent periods, it grows. So AL1 is 1 plus theta. And AL2 is 1 plus theta squared, and so on. And theta is 1. So it basically means that productivity doubles every 20 years. Okay. So, what's going to happen? Well, hopefully you can easily work this out. In the first period, L is 1, AL is 1, ALL is 1, so R will be 1. Okay? So basically, people are just going to, this is free, these firms, they're just going to grab whatever they need. And in the first period, they need 1 unit. In the second period, AL has become 2, ALL is 2, so they're going to grab 2 units. In the third period, AL has become 4, it's doubled again. So ALL is 4, and now they're going to grab 4 units. In the fourth period, AL is 8, ALL is 8, they're going to want 8 units. But we've got a problem because there aren't 8 units left in the stock. The barrel has run dry, and the economy collapses. Okay. So what's wrong with this? Well, we'll have a talk about that on when we meet, and hopefully you can think about it now, and you should get some input to that when we think about the DHSS model, which was basically developed as a response to this, and a bunch of other things like the oil crisis, which was also in the early to mid 70s. Okay, I think that'll do for this video.